Welcome back. In the last part of this section, we're going to take a look at a very important differentiation technique called logarithmic differentiation. This is extremely useful whenever we've got a function that's one gigantic product or a gigantic quotient. So the idea here is that if we had a function, we could take natural log of both sides and differentiate both sides implicitly, and that's of course fine and allowed. The reason why we might do that is when taking natural log of both sides, maybe those log properties will allow us to simplify the right side of our equation, making our derivative easier for us to do. So that's kind of the same thing that we were using as sort of in the background when we had something like this nasty function. I used log properties and that made that function less terrible, and differentiating it was pretty easy. And we're going to do that for a function that doesn't already have a log involved. So something like this, y is equal to this gigantic product. If I wanted dy dx and I wanted to do this directly, I would have a product rule inside of a product rule inside of a product rule, and there's also chain rule involved as well, functions inside of a function. Instead, the plan here is I'm going to start by taking log of both sides of the equation. So natural log of y is natural log of all of the right side. And of course, if it's natural log of all of the right side, then I can use that log property to simplify what I've got. So I can say that I'll have on the right side now three logs added together with powers taken down in front. So I can say that natural log of y is 3 natural log of x squared plus 2 plus 4 natural log of x minus 1, and then plus 7 natural log of x plus 5. And now if I wanted to differentiate both sides with respect to x, on the left side, natural log of y, its derivative would be 1 over y times the derivative of y, dy dx. And on the right side, I would just have 3 little logs to differentiate. I would have 3 times 1 over x squared plus 2 times the derivative of x squared plus 2, which is 2x, plus 4 times 1 over x minus 1 times the derivative of x minus 1, which is just 1, plus 7 times 1 over x plus 5 times the derivative of x plus 5, which is just 1. So I've done all of my little term-by-term differentiation, and then now to find just dy dx by itself, I only need to bring y up to the right side, and so dy dx is just now y times 6x over x squared plus 2, and 4 over x minus 1, and 7 over x plus 5. And then the last thing that I can do is I can notice that y is my original function. So if I wanted to actually have a nice explicit way of writing dy dx, good news, I can, and it will be just my original function, x squared plus 3 cube x minus 1, 4, x plus 5 to the 7, all multiplied by that gigantic bracket. I'm not going to do anything else with this. I mean, you certainly could if you felt like it, and I don't really think that that's a super profitable thing to do, but you could always combine these 3 terms to make one giant rational expression, and then combine it all together to make one giant rational expression. More than likely, if you are finding a derivative, you're going to be doing something with it, and so leaving it in this form is probably good enough. So here's a sort of an older problem. This is one that we could have tackled back in chapter 2. I mean, this is a quotient. There's a little bit of a chain rule going on as well, because inside of our quotient we've got a square root and things raised to powers. But we're going to see that actually, if you wanted to compare how much work it would be quotient rule with using logarithmic differentiation, this is going to be so much faster and easier. So first off, same as before, if you're looking for an equation of a tangent line, it makes sense to find your point. So I'll do that over here and say for the point, if x is equal to 6, then y would be 6 minus 7 cubed over square root of 6 plus 3. 6 minus 7 is negative 1, cubed is negative 1, and 6 plus 3 is 9, and square root of 9 is 3. So looks like we'll have negative 1/3. Okay, so 6 negative 1/3 is our point. And then as far as finding the slope goes, that's our next part, I need to find dy dx, and I'm going to do differentiation logarithmically. I mean, I could do quotient rule, but instead I'm going to say that if I took natural log of both sides, I would have natural log of y equals natural log of the right side, and I know how that would simplify. It would be 3 natural log of x minus 7 minus half natural log of x plus 3. And if I differentiate this with respect to x, I'd have on the left side 1 over y times the derivative, dy dx, and on the right side I'd have two little quick derivatives to find. 3 times 1 over x minus 7 times the derivative of x minus 7 minus 1/2 times 1 over x plus 3 times the derivative of x plus 3. And then the last thing I would want to do is bring up my y to have dy dx, and it would be y times 3 over x minus 7 minus 1 over 2 times x plus 3. So one thing I'm not going to do, which I did in the previous one, so previously when I found the derivative, I then back substituted. I took my original function y and stuck it back in. Here I'm going to be evaluating what is my derivative at x equals 1, and the thing is, at x equals 6 rather, and the thing is, I already know what the y value is when x is 6. We already figured out that when x is 6, y is negative 1/3. So if I stuck this whole function back in and put 6 in, I would get negative 1/3, and I already know that I would get that. So in this case, it makes more sense just to leave things as they are. So at x equals 6, you can say that the derivative would be the y value that we just found, that's negative 1/3, times 3 over 6 minus 7, which is negative 3, minus 1 over 2 times 6 plus 3, that's 18. If you run that through your calculator, you'll get that this turns out to be 55 over 54. And so now to finish things off, we just need to now create our equation of our tangent line, and that's not hard to do. Now that we've got our point in our line, we can say for point in our slope rather, for the tangent line, it's y minus the y coordinate equals our slope times our x minus our x coordinate. And then if I clean that up, so bringing the 1/3 to the other side and expanding, I'll have y is equal to 55 54ths x. 55 54ths times negative 6, and then minus 1/3 gives me minus 58/9. And there we go. There's my equation of the tangent line to our curve. Now, for the last two problems that we did, I mean, they would be irritating to do without logarithmic differentiation, but they'd still be possible to do. So if you really wanted to, you could do this with quotient rule, and for the previous one, you could have done it with a bunch of product rules. But you can have functions where you don't really have much of a choice, and this is one where we don't really have much of a choice. Our function is x raised to the power of x. So before you get any clever ideas about using power rule here, no, you can't, because the way that the power rule was defined was it was defined for a function that was x raised to some irrational power n, where n was some sort of a constant. So if that were the case, then you could use power rule, and I would be happy about that, and I would celebrate your choices. However, if we're looking at x to the power of x, x is not a constant, x is a variable, which means power rule does not apply here. So if you were to try to apply power rule and say it's x is coming down and we're reducing the x by 1, I would say that's a bad choice. Instead, though, if we took the natural log of both sides of the equation, that actually does do some good things for us, because we'd have natural log of f of x, and then we'd have natural log of x to the power of x, and then we could take our x down in front, and now we'd have something we could differentiate with respect to x. And there'd be a little bit of a product rule on the right side, a little chain rule on the left side, but nothing too terrible. So differentiating with respect to x, on the left side, derivative of natural log is 1 over whatever its natural log of, and the derivative of f with respect to x is f prime. On the right side, I've got a little product. First thing as it is, derivative of the second, second thing as it is, times derivative of the first. So now we're pretty much finished, because I have f prime divided by f itself is 1 plus natural log of x. And so that means f prime is the original function, f of x times 1 plus natural log of x. Or in other words, x to the x times 1 plus natural log of x. And there we go, we found our derivative. So this is one where you really wouldn't have a choice. If you had a function involving x's to powers that also involved x's, then logarithmic differentiation is going to be the way to go. Okay, one last little thing to talk about before we end for the moment, and this is sort of a domain issue that we've been having. We know natural log of x, its domain is x itself would need to be bigger than 0. So if we had a composite function, natural log of some function of x, then f of x would have to be bigger than 0, which is not something that is super nice for us. It would be lovely if we could just exclude the places where f of x was 0. Like if we could look at natural log of absolute value of f of x, that would make our lives easier, because instead of maybe having huge intervals that we have to ignore, we could just maybe take a few places where f is equal to 0 and ignore them, and every place else would be great. But then the big question that you have would be, like, how is that going to affect the derivative? Because if we were interested in this function and we wanted to sort of make our domain bigger by slapping on absolute values, hopefully that doesn't do terrible things to our derivative. Good news, there is no effect on the derivative. So we saw before, if you had a function u of x, that its derivative for natural log of u of x was just 1 over u times u prime, and that's actually the same when we've got natural log of absolute value of u. So as long as u is not equal to 0, then we can take that derivative, which means that that we can now extend our domains for natural log of some function of x by putting absolute values on. As far as the proof goes, it's not really that hard to do, because we know that if we're talking about absolute value of u of x, we're talking about really a piecewise defined function. It's going to be the function u of x if u is bigger than or equal to 0, and it's going to be the function negative u of x if u was less than 0. So if we're talking about the derivative of natural log of u of x absoluted, then we're going to have to look at it sort of in two halves. So I'll say first off, if we're talking about the places where u is bigger than 0, then I know natural log of absolute value of u of x is natural log of just plain old u of x. No absolute value needed. And so therefore the derivative of natural log of u of x absoluted should be the same as the derivative of natural log of u of x. And an earlier theorem told us that if you were doing that derivative, it would be 1 over u of x times derivative of u of x And so therefore we've got u prime over u, and there we go. That's the derivative that we get if u was positive, which again, not a big surprise. We're going to see that if u is negative, we get the same conclusion, and that's kind of the nice part about this. So now for the second half of this, we just say, well, if u is less than 0, then we're going to say that, again, natural log of absolute value would be natural log of negative u. So natural log of absolute value of u of x would be natural log of negative u of x. And if we were doing the derivative of both functions, the derivative of the left side, the derivative of natural log of absolute value of u of x, that would be the derivative of the natural log of negative u of x. And then I'm just going to use chain rule here and say, well, it would be 1 over the negative u of x, and the derivative of negative u of x would be negative u prime of x. And of course, the negatives would cancel out just lovely, meaning that at the very end of it all, I get exactly the same derivative. I get u prime over u. So that's basically our end of our proof. It really doesn't matter if we're talking about positive values of u or negative values of u. In either case, the derivative of natural log of u of x was just u prime over u. So now that makes our life a little bit easier for this. I have a function natural log of this absolute value of secant plus tangent. So I know then for my derivative, I don't have to really worry or care all that much about the absolute values. I can just say, well, it should be 1 over whatever's inside the absolute value multiplied by the derivative of what's inside the absolute value. Derivative of secant is secant tangent. And the derivative of tangent is secant squared. And so I'm going to clean that up just a little bit. We get secant tangent plus secant squared over secant plus tangent. And one thing you'll notice here also in the numerator, I can factor out a secant. And when I do that, I get secant of x times tangent plus secant all over secant plus tangent. And if we're looking really carefully, we'll notice we actually have a common factor top and bottom. The secant plus tangent cancel, giving us just secant. So actually kind of as a fun little surprise, in a way we figured out the antiderivative of secant is natural log of secant plus tangent absoluted. So we're going to see for some of our trig functions that they're antiderivatives, specifically secant and also cosecant, tangent, and cotangent, that their antiderivatives will involve natural logs. And we're going to see that in the next section.